Here in Chapter 8, we're going to be looking at some interesting applications of integration. And in particular, we'll be looking at some interesting geometric applications related to arc length and surface area. So let's first consider the problem of finding the arc length of a curve. So the problem is we're given a curve that's defined by some function f of x on the interval from a to b, and we want to find the length of that curve. So the way we can approach it is we can start with an approximation using line segments. So we break the interval from a to b into subintervals. So we partition the interval, which creates a sequence of points P1, P0, P1, P2, and so on. And then we find the length of the segment from P0 to P1, and then the length of the segment from P1 to P2, and so on. And then we just sum the sum the lengths of each of these individual segments. So doing that would give us an approximation of the length of the curve. So as we increase the number of these approximating line segments, for instance, if I take the limit as n approaches infinity, where n is the number of these line segments, we'll get progressively better and better approximations which will approach the true length of the curve. And hence, we can define the length of the curve as the limit as n approaches infinity of the sum of these individual lengths. So what is this notation? Pi minus 1 pi in absolute values. This is just the length of the segment connecting pi minus 1 to pi. So in other words, it would be the length of this segment here, for instance. So if we sum them up over all these points, okay, that would give us our approximation. And so taking the limit as the number of those approximating segments approaches infinity, we get the true length. So in fact, here we can write this as a distance formula, right? So if I'm looking at, say, this ith segment here from pi minus 1 to pi, we can use the distance formula. So it would be the change in, so the distance formula, we know it's going to be the difference in the x coordinates. So say xi minus 1, or sorry, xi minus xi minus 1 squared, and then the difference in the y coordinates, say yi minus yi minus 1 squared. Okay, which is really just now something we can approximate using here, let me write this as delta x, because in general we're going to be breaking this into equally spaced subintervals, so we're assuming that they're all a distance of delta x apart. And so we can assume here delta x is going to be the same for all the intervals, and then delta y will be different for each interval, but can be written as a function of delta x. So let's see what we can do to approximate that further. So we know that here the pi minus 1 pi distance is equal to delta x squared plus delta y I squared. And here I'm going to write delta y in terms of the f of x. So it'll be f of xi minus f of xi plus delta x and we can use the mean value theorem which asserts that there is some xi star in the interval from xi minus 1 to xi such that f of xi minus f of xi plus delta x is equal to f prime of xi star times delta x. So this is from the mean value theorem, and therefore we know that there is some xi star such that this is equal to delta x squared plus f prime of xi star times delta x squared. And then here, if I factor out the delta x from these two terms, we have 1 plus f prime of xi star delta x squared. And then the delta x on the outside of the square root is no longer squared because we are taking it out of the square root. So here, let's put it together. Now we're taking the limit as n goes to infinity of the sum from I equals 1 to n of these individual approximating lengths. And what we've shown here is that the length, pi minus 1 to pi, can be written as the square root of 1 plus f prime of xi star, where xi star is just some point in between xi minus 1 and xi. Okay, which we know that this value is going to be a Riemann sum of a particular function, and oh, I should be careful, this is squared here. So it's the Riemann sum of the function square root of 1 plus f prime of x squared on the interval from a to b. So this will converge to the integral from a to b of the square root of 1 plus f prime of x squared. And now we have the formula for finding the arc length of the curve on the interval a to b, which says here if f prime is continuous on the interval a to b, then the length of the curve y equals f of x for x between a and b is L equal to the integral from a to b of square root of 1 plus f prime of x squared dx. So let's practice this with an example. Suppose I want to find the length of the arc of the semi-cubical parabola y squared equals x cubed between the points 1, 1 and 4, 8. Okay, so here's just a picture of the segment that we're going to try and find the length of. Now let's first solve for y in this equation. Since we know that y is in the part of the graph where it's positive, we can write this as y equals the square root of x cubed, which is really x to the 3/2 power. And hence we can also get y prime as 3/2 x to the 1/2 power. And then putting this into our arc length formula, in this case going from a to b, we're going to go from 1 to 4, the values of x, and we're going to do the square root of 1 plus, here our y prime was 3/2 x to the 1/2, quantity squared. Okay, so that's, I'm just using my arc length formula. Okay. And let's try and work this out. Inside the square root we have 1 plus 3/2 x to the 1/2 squared becomes 9/4 x. And then I can solve this with a simple substitution. So I'm going to let u equal to 1 plus 9/4 x. So we get du is 9/4 dx. So the integral becomes 4/9 integral of the square root of u du. I'm also going to change my limits of integration here to match the new variable. So when let's write it over here. So when x is 1, we get u is 1 plus 9/4. So that would be 13/4. And when x is 4, we get u equals 1 plus 9/4 times 4, so that's 1 plus 9 is 10. So my new limits of integration will go from 13/4 to 10. Okay, and then it's a simple integral. U to the 1/2 power integrates to 2/3 u to the 2/3. So yeah, we have 4/9 times 2/3 u to the 2/3. Sorry, u to the 3/2. Sorry, I'm mixing it up there. So so the integral of u to the 1/2 power, we'll add 1 to the power, so we get a power of 3/2, and then multiply by the reciprocal 2/3. And let's continue here. So 4/9 times 2/3 will be 8/27. And then we have 9 to the 3/2 power minus 13/4 to the 3/2 power. Okay. We could of course do a little bit more simplification here, but I won't go too far with it. Noticing that here 9 to the 3/2 power is just 27. 13 to the 3/2 over 4 to the 3/2, which is 8. Okay, so we'll leave it there. And one thing we want to keep in mind is we can also use the same formula when we're integrating with respect to y. Okay, but one thing we have to keep in mind is that here we're given the function x equals g of y, and we're given the values of y that give us the endpoints of our curve. So notice that the endpoints here, c to d, are going to be the y coordinates. So let's demonstrate with this example here. Find the length of the curve given by y squared equals x from the point 0, 0 to the point 1, 1. Notice here we have x defined as a function of y. And so x prime would be 2y. So let's write now the integral from 0 to 1. And notice there I'm using actually the y coordinates, not the x coordinates, even though they're the same. The square root of 1 plus 2y squared dy. Okay. Which gives me the integral from 0 to 1 of the square root of 1 plus 4y squared dy. How do I integrate this? Now this might be something we need to go back to remind ourselves how to integrate using like a trig sub or something from chapter 7. However, let's see what would happen if I did it the other way. So this is integrating with respect to y, but suppose I wanted to do it the other way and integrate with respect to x. Well, I could isolate the y in the equation, get y equals the square root of x, and then y prime would be 1 over 2 times the square root of x. So let's notice that here we can get the same arc length using a different variable. So I'll do the same integral from 0 to 1, right? But now I'm going to be using the x coordinates there. And now I'm going to be using, this is my y prime. So our integral in this case would be square root of 1 plus 1 over 4x. So actually comparing these two, maybe it's a little bit less clear how to approach this example or this version of it. So in my experience, since I know the technique I want to use here, which is a trig sub, I can substitute y equals 1/2 tan theta and do a trig sub, and I know that's going to be in the form where it'll simplify and we can get a value. Okay, so I'll leave you to fill in the remaining steps there.